Hello again. So today we're going to get started on chapter 2, root finding. I've just scribbled above my head here in the lecture notes, and we're going to revisit some familiar things probably today, but also show how we're going to take it a little bit further than you did last year in terms of analysis of convergence. That's a key idea. Okay, so if I just flick over to my board, I'm going to disappear from view now, to make best use of the space so I can use all the board, and I'll come back a little bit later. So let's see. Okay, so chapter 2, root finding. So consider function f to solve the problem f of x equals 0. Okay, so in general, this is not a soluble problem. There are specific cases that we're all very familiar with. When f of x is a quadratic, we've got a formula for solving it, but in general, if f of x is a particular nonlinear function, we can't solve it, so we need to find an iterative method. So we need to iterate to the true solution. And true solution is x equals x star. And so we're just getting used to now the notation I'm going to use in this module. So each iteration is given by x subscript n. Okay. And if the method, and so n is an integer, if a root finding method converges, that means xn tends to x star as n tends to infinity. Okay. That's what we wish to find. But before we just revisit some of these root finding methods, just a note on the notation. So we've got a true solution. Okay, so we assume there's a true solution always. And in a lot of the examples in this terms part of the module, we will also know what the true solution is for many of the problems we'll look at, and we'll be able to see if it converges to it. So that's the sort of notation that with the asterisk there. And then the iterant, if that's the right word, the bit in the iteration is given by x subscript n, and we assume it tends to x star as n tends to infinity. Last year you may have put the n in the superscript and put a bracket around the n. It's more convenient for just single dimensional problems just to have it in the subscript. That's what we're going to do. And this idea of convergence, again we're visiting familiar problems here, is one that will come up again and again. So whilst it's a familiar problem, the concepts, I just want you to flag quite clearly what the concepts are, so we can take note of that as we go forward. And we are going to consider what is called bracketing methods to begin with. Particularly, we're going to look at bisection. So the aim of this module is not to fill your head with lots of methods. If I did that, I would double the number of methods in here. The aim of it is to use a smaller subset of methods so you can learn and understand how they converge, when they work and when they don't, and how fast they converge. So bracketing methods, this is now section 2.2 of my notes. It's a robust way of ensuring convergence. It's when 2 points at step n of our iteration, let's call them an and bn, bracket the root. So let's just draw a little diagram to illustrate that. This is our function, it could be anything. Actually, let's just do it with a single root here, unambiguous. So this is our root x star here, and this is our axis x. And what we're saying at any point, if we lay down an and bn, they lie either side of the root. Okay. And if you have a method that's a bracketing method that ensures that a and n are either side of the root, it will always converge. So this is a robust, these are robust methods, not necessarily the fastest, but they're robust methods. It's bracketing methods, and bisection is one example of that. So when we do this, we're using a theorem, and we're using what's called intermediate value theorem. And I'm going to state that next. Okay. So that's what I aimed at. This is not a pure mathematics course, but there are theorems that underlie the methods, and I want to, when a theorem is appropriate, I will bring it up, and that helps us understand the sort of mathematical structure that underlies numerical methods. So it's called Theorem 1 in the in my notes, and it's the IVT. And it states this: if f is continuous on a, b, so you should be familiar with this notation. This means a closed interval, so interval that includes the endpoints. If it was an open interval, it would be curved brackets, so a closed interval a, b, and also if f of a times f of b are less than or equal to 0, then there exists a root x star which lies in this closed interval a comma b such that f of x star equals 0. So we're not going to need to prove this, but I will give you an illustration that shows how it works. It basically says if you have a continuous function, a little bit like the one we've had before, and we have 2 points a and b, f of b in this case, sorry, I'll do that a bit clearer. Let me redraw that. Just draw b a little bit further down there. So f of a is greater than 0, f of b is less than 0. If it's continuous, they're at least, and in the most examples we use here, we use examples where there's just one root in this interval, but it, strictly speaking, means there's at least one root in this A and B. So this is the theoretical basis. When you try and find a root by a numerical method, we can establish first of all that a root exists by the intermediate value theorem, that the function has opposite signs either ends of the bracket. Yeah, so in this case, f of a times f of b, that's the quickest way to clarify the opposite side is less than 0 here. So therefore the root exists. Okay. And I'm told that this proof of this theorem is in an analysis module out there. But the basis of the proof would be this this picture that I'm showing. And this applies in one dimension. So even before we fling our numerical method at this, we've got a way now of establishing that the root exists. Okay, and now we can proceed to find that root. Okay. So the particular bracketing method we're going to use is we're going to consider bisection, which I suspect you've come across before, but we're revisiting it, highlighting key aspects of numerics, also trying to go deeper in our sort of understanding and what are the theorems underlying the whole thing. So bisection is as the method implies. And actually, before I write it down properly, let's consider how we do it. Basically, we start with our initial bracket that we consider the roots in this first bracket initially. Yeah, and then we bisect it. So we basically take the midpoint. That's our bisector. And then we test either end. If let's say the root lies somewhere in there, that means when we bisect that interval, we can discard that section, and then we proceed to a new interval that we know brackets the interval, and then we bisect again, and we continue. Say the roots, say the root lies there, we just discard that one. So that's the picture. Okay, you just have the interval, do an if test essentially, and we'll look at this method, this type of method in the practical, and then proceed onwards. And because it's a bracketing method, we know it will converge to the roots. Even if it doesn't converge that quickly, it will converge to the roots. So that's the picture. Let me just write down sort of the steps now. Bisection. So the first step is we set our initial bracket. Just checking that I'm recording. Set initial bracket, and we call that actually we're going to index our initial n as 0. Okay, that's a fairly arbitrary choice between 0 and 1, but we just chose it 0 in this case. So we're going to set A0 is A, B0 is B, and then we're going to bisect. So, and we're going to give C of n. So at any one point we have A of n, B of n, and then we have the bisector, which is C of n. Okay, little diagram on the top right. And Cn, of course, is simply half of an plus bn. It's just the bisector. And then the main decision making of this method is select the new bracket. And we use our friend the IVT, the intermediate value theorem from that was stated a few slides ago. So if f of a of n, f of c of n less than 0, so that means, let's just draw the diagram. That means that the function at either side of a of n, use a cursor here, area of c and n are opposite. It means the root must be in here. We select our new an, so an plus 1 equals a of n, and then b of n plus 1, our new b is c of n. So that's just the numerical way of saying what we just draw diagrammatically, that we're rejecting this bit. So we just use the IVT to check the function either side 0. So this is where it comes in, and it's always come in the root finding method. So let me then just write out the other opposite case. So the opposite case is where you have Cn, b of n there, and a of n, and the root lies in there. So that in that case, that means f of c of n and f of b of n are opposite signs. So f of c of n times f of b of n is less than 0, and we then select Cn, Bn as our new bracket, or another way of putting it is an plus 1 equals c of n, b of n plus 1 equals b of n. And bisection is robust. That's the main advantage of it. So we'll always converge. But how fast does it converge? Can we quantify this? So this is an example, I think, where this module takes over from last year. You would have maybe computed this method, but maybe you've not been quite so careful about answering this question, how fast it converges, how it compares with other ones. So that's what we're going to do. Now it's quite a we've decided to try and keep these videos like about 18-20 minutes, and then we'll restart. So what I'm going to do then is I'm going to stop this video and restart with sort of our first bit of convergence analysis, our bisection method. And this is going to be a theme, as I said, that's going through a whole module. Certainly this term is that we're going to try and quantify the convergence for each method we do, and that's really where the mathematician comes into its own. So and let me see it scrawled all over the top of me. So this is me again, just signing off for this video, but saying see you in the next one, where we will continue with convergence analysis of the bisection method. So see you then. Bye for now.